So here, a particular ionic compound is written as AB2. So if you if that dissolves, most likely to become A2 plus, and then B2B minus, right?
Yes.
And the KSP of the substance is so KSP is 1.39 times by 10 to the power of negative 8, and this would be molarity to the power of 3, true? Because the QSP is a product of A2 plus and then a B minus to the power of 2, right? So that's molarity squared, so it's molarity 3. Anyway, calculate the solubility of this substance in mole per liter. Okay. So we want to know how many of this dissolves per liter. Okay. In your calculation, follow the steps below and write your response. Okay. Right. Write an expression showing the dissociation of this compound. So that's this one here. Don't forget to put solid there and an aqueous there and an aqueous there. So that's question A. Now you write expression for KSP. So I guess they want you to do that one.
Yeah.
Equals to 1.39 times by 10 to the power of negative 8, right? Maybe they want that. I don't know. So it could be 2 of this, or that, or all of this.
Cool.
C, construct an ice table and fill it in a table appropriate. Okay. So in this case is a much easier version of question A. So this is that version, the water version of the question.
Yeah.
Okay? There's nothing else. There's no already existing solution. It's just water. So they just want to know the Ks, the solubility constant. So you got to know the difference between solubility constant.
Yeah.
That's KSP, but the solubility. So you see how KSP is an m to the power of 3?
Yeah.
The unit for that is m3. But then the solubility of this solubility of the solid is always in just m. Okay?
Okay.
Yeah.
But what about moles per liter?
That's the moles per liter. M is the moles per liter. Isn't it? This is the mole to the power of 3 divided by liter to the power of 3.
Yeah.
This is ice table and fill it up appropriate. Okay, so we have the A, B2 becoming A2 plus and then a 2B minus. Initial, there is a certain amount of this, we just don't know, and 0, 0, right?
Yeah.
We just don't care about this column really. Change, this will, because this is going into pure water, of course some of this stuff will go into that and that, so this will be like
So it's
the
minus
question mark minus x, and this will be plus x and plus, sorry, this will be just minus, because it's change, right?
Yeah.
This will go down by a certain amount, plus x plus 2x. And then the equilibrium will be this minus x, and this will be x, and then 2x, of course. And just need that and that in this equation, right? So just need x times by 2x squared, and that's equal to 1.39 times by 10 to the power of negative 8, right?
Yeah.
So this will be 4x to the power of 3 equals to 1.39 times by 10 to the power of negative 8. I think I saw that number there, sort of. So that's 1.3. That's 1.4, right? So this is exactly question 8. This is 1.4 there, you see? Times by 10 to the power of negative 8. This is 1.39 times 10 to the power of negative 8. And exactly the same type of compound, isn't it? Yeah, so you get x is equal to 1.39. 1.39 times by 10 to the power of negative 8, divided by 4, and then the cubic root of that. That's 1.5, 1, negative 3. And that's exactly the same as this water case, isn't it? 1.5, 1 times 10 to the power negative 3. Very similar value.
Yeah.
Now, when they are talking about the solubility, so let me just do that in green color. Solubility of this substance, of this metal, of this salt in mole per liter, they're talking about this value here. How much dissolves, okay?
Right.
Yeah, how much dissolves. So what that value means is that when this solid goes into the water, you're going to have 1.51 times 10 to the power minus 3 mole per liter of that substance.
Yeah.
And then double that, 3.02 times by 10 to the power minus 3 mole per liter of that amount. But then if you combine that,
That's KSP.
yeah, of course, the multiplication of those two will give you the KSP. But then if you have that many moles per liter of that and that many moles per liter of that, you can say that 1.51 times by 10 to the power minus 3 moles per liter of that is dissolved. Understand?
Yeah.
Because
Oh, okay, I see.
yeah, if you just ignore the moles per, think about it. If you have that many mole and that many mole,
Yeah, and you
they
just
combine to give that many mole, right?
Yeah.
Of that. That's why you can. That's what it means by the solubility of this solid. How much of it is dissolved? You see, that's what they're talking about.
Yeah. Okay, I get
So
it.
solve your equation to find the solubility, right? So that's why you see how in this question also they're missing the volume. They don't talk about volume, right? They just talk about concentration. But I think it's better understood, I think, this way. So I'm just going to actually copy this again and do it over here as well. So it's going to be exactly the same thing, but this ice, you see how this ice table used to be the concentration? But what I'm going to do now is every number here is just going to be the number of moles instead of moles per liter, okay?
Yeah.
So the KSP is 1.3839 times by 10 to the power of negative 8 mole per, that's m to the power of 3. We already talked about that this is m to the power of 3, true?
Yes.
And we're going to assume that there's a beaker, this is a 1 liter, and this solid, enough solid is going to go in there, okay? Solid is going to go in there, and some of the solid will dissolve, right?
Yeah. Yeah.
Now, initially you have AB, certain amount of AB, but we don't have the, yeah, we just don't care about this, but we're just going to write it anyway. And that's A2 plus and then B, 2B minus. Now, there's 0 mole. So instead of molarity, instead of moles per liter, I'm just going to do how many moles are there, okay, in this liter. Because once you figure out how many moles are there and then divide by liter, then you get the concentration anyway. That's why I'm assuming that there is a beaker with containing 1 liter of water. So there's 0 mole here. Let's say you have like, I don't know, 400 grams of this solid, whatever, okay?
Yeah.
So there's like 100 mole, let's say. A lot of them available, okay? Now, certain number of mole, so X number of mole will be used and be converted into those two, true? So if X mole of that is dissolved, is gone, and turned into those two, how many mole of A plus will be, 2 plus will be produced? It'll be X mole, true?
Yes.
So if X mole of that is dissociated into those two, you get X mole of that. So like, for example, if you have like -1 mole, then you get 99 mole, right?
Yeah.
And let's say then you get 1 mole of that and 2 mole of that, right?
Yeah. Mm-hmm.
And this will be 1 mole and 2 mole, true?
Yeah.
Now let's suppose that this actually happened. Okay. Let's say
Okay.
this actually happened. What would be your KSP?
1 times 2 to the power of 2.
That's right. It'll be 1 times by 2 to the power of 2, which is equal to 4, isn't it? That'll be your KSP, and this will be. However, you got to be careful. You see how this is mole and mole. This is not mole per liter, right?
Yeah.
But you see, because we assume that this is 1 liter, you can just change that to you can just change what's the concentration of the A2 plus. It'll be 1 mole per liter, right? You can only put concentration in here. This will be 2 mole. There are 2 moles that are produced, but it's existing in 1 liter, so you can just divide by 1 liter and you get concentration. So you still get the same answer, 4 mole, 3 per liter 3. So that's why there's a 4 molarity to the power of 3. True?
Yeah.
Do you
Oh.
see?
Mm.
So that's why it's better. It's much easier to understand through just having mole there. And then when it comes to the KSP, you just have to divide by liter. It's interchangeable, right? From mole to liter. If you have 1 liter, it's between mole and molarity, it's interchangeable. And it's far easier to understand it this way. Now, this is the KSP, but what is the solubility? What is the solubility of the solid AB2? But you see how there were 100 moles, but then you were able to dissolve 1 mole?
Yeah.
So the answer is there's 1 mole dissolved in 1 liter. So the answer is 1 mole per liter. Understand?
Mm-hmm.
That's the solubility. That's what they're asking for, the solubility in mole per liter.
Oh.
That's different from this number.
Yeah, yeah.
Okay? So it's exactly the same situation going on, but except that, of course, here I chose 1 mole, 2 mole, and then of course that does not give you that number. But whatever it is, this has to be negative x mole. And when x mole of that dissolve, then you're going to be producing x mole of that and 2x mole of that, right?
Yeah.
And then you're going to end up with negative 99 minus x mole left. And then you're going to have x mole here and then 2x mole here, right?
Mm-hmm.
And of course, because we are assuming that this is all in 1 liter, that just goes in there. So we can form x mole per liter and then 2x mole per liter square is equal to 1.39 times by 10 to the power of -8. Then you get x is equal to, like we calculated before, 1.51 times by 10 to the power of -3. What that implies is, just do the ICE table again. There was 100 mole, 0 mole, 0 mole. You're going to be consuming 1.51 times by 10 to the power of -3 mole, and you'll be having that and that, 2 of that, right? So you'll be producing 3.02. Are you still there, Natalie?
Oh, yeah.
Yep.
Yeah. Mm.
And of course, this will give you pretty much roughly equal to 99 still, 100 mole still. And it'll be just that and that still here. Mm-hmm.
Yeah.
And that satisfies, that times by this one square will satisfy that equation. And the question of what is the solubility of AB, you know how this number was the solubility, right?
Yeah.
Yeah. So just this is the answer. That's the solubility. That many moles of the solid is dissolved in 1 liter. So therefore, the solubility of AB2 is 1.51 times 10 to the power minus 3 mole per liter. Okay.
Okay.
Yeah, but obviously it's far easier to understand
Yeah.
this stuff, right? If it's so, that's what I'm talking about. If there's the volume, if there's no mentioning of volume, assume there's 1 liter, and just say these are all just number of moles. Okay.
Yeah. Okay.
Yeah. Yeah. All right, we'll call it a day here. So I think this will be like the hardest type for I think tomorrow's Monday's